It's there's a link to a YouTube channel on Canvas, the front page of Canvas, and then it has a link, and then it has all the videos on there. Okay, so make sure you guys like the video, smash the subscribe button, join my Patreon and my Discord. Okay, especially the Patreon, and I'll put your name at the end of every workbook so you guys can get credit. No, I'm just kidding. I'm just kidding. I don't have a Patreon. I should start one though. All right, so we'll talk about gases. So I know that you guys are probably familiar with gases from, just other science classes, and because we do encounter gases on a daily basis, right? Now, there are a couple of properties of gases that make them different from solids and liquids. You guys probably know this already, but I just want to go over them. And again, you don't need to write this down. So when you have a mixture of gases, right, they kind of behave physically like one material. So the air around us is a mixture of a bunch of different types of gases. We got nitrogen mostly, got some oxygen, carbon dioxide, argon, water vapor, got different types of gases around us. But when you kind of just look at the gas mixture around us, it's kind of like the same thing, right? And so that's one property of gases. A big important one is that they expand to fit their container. So that's why when you put gases, so like if you fart in a corner of a room, right, in an enclosed room, and you know how slowly that smell travels from one side to the other, that kind of demonstrates that they expand to fit their container, right? And so the container will be the room, and then the gas molecules move around and they expand. Okay, gases are also highly compressible. So you can compress gases. That's why if you have like an aerosol bottle, you press the button, a lot of gas will shoot out, right? And that's because you can compress gases. Okay, and lastly, gases form homogeneous mixtures regardless of their identities and proportions. What that means is, doesn't matter what the ratios are or what types of gases you are, when you kind of look at them, it'll make a homogeneous or kind of uniform mixture. Yeah, what's up?
And what's like plasma? Do we ever have to deal with that?
So plasma is a different type of matter. I'll briefly go into, how if you heat up a solid, melts and turns into a liquid, you heat up a liquid, it vaporizes, turns into a gas. If you heat it up even more, the nucleus of the atom starts moving faster than the electrons. And then, so that's what a plasma is. Plasma is basically where it's moving so quickly that the electrons and the nuclei are no longer moving together. Yeah, but we're not going to have to deal with that in this class. Good question, though. Okay, so one key thing that you guys do need to know is that when you have a gas, the actual molecules only take up about 0.1% of the total volume. So let's say I have a balloon, right? This is my balloon. There will be very few actual gas molecules in there. Okay, like it might take up a lot of space, but there's very few actual gas molecules. The reason they're able to keep that shape is because they're constantly flying around and they're bouncing off the containers of the balloon. But just know that the actual molecules take up very little space inside of the gas. Okay, and the reason why that, like in a balloon, they're able to keep its shape is because even though there's very few, they're constantly bouncing around the walls. Okay, which kind of segues into the first property of gases. And you guys probably want to write this down, is pressure. Okay, we observe or we quantify a lot of properties about gases based on their pressure. And pressure is just basically, it's a formula. We're not really using this in chemistry, but it's the amount of force you have in a given area. Okay, so gases, they exert pressure because again, we said gases are flying around. So if I have a container, gases fly around and they bounce off the walls of the container. Okay, so in this classroom, the gases are bouncing off the walls. They're bouncing off you right now. It's going beep, 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 and it's like hitting you right now. And that's what the pressure, that's what we call pressure. Okay, so first property of gas is their pressure. And it's basically, think of it as the collisions they make against the walls of the container or the things around it. Yes, you are constantly being bombarded by gas molecules. Every second of every day, you are under attack. Okay. So that's the first property, pressure. Down, and this kind of a little figure to help demonstrate that they bounce off the walls. And so you can have low pressure, which is when the gas molecules are not colliding, right? If you have a big container and a little bit of gas, there's not going to be a lot of pressure because it's not bouncing off the walls more. But if you make the container smaller, right, if you decrease the volume, it'll be bouncing off a lot more, and that will increase the pressure. Yeah.
Let's say there's like a crazy amount of pressure, like the gas molecules like revert back to like liquid.
Yes, it can. Yes. Yeah, you can, if you increase the pressure enough, it can turn it back into a liquid while keeping it hot. Yeah, very interesting, but we'll get into that later. Okay, so just like how we do in chemistry for basically everything, we measure pressure with numbers, right? And if we have numbers, we need units of measurement. Okay, so a typical way that we calculate or measure units of measurement is with the Pascal. Now, Pascal is equal to 1 Newton per meter squared. Okay, we are not going to be using Pascals that often, and we're not going to be using Newtons per meter squared, but that's kind of the base measurement. We'll actually be using these more. So when we study gases, we use something we typically have to measure based on a standard. And we call the standard a standard atmospheric pressure. And that's basically the typical pressure at sea level. So Long Beach is next to the ocean. And so this is very similar to what we have, that gas molecules around us give about a pressure of 1 atm. Atm is atmospheres, not at the moment. And that's equal to 760 millimeters of mercury, 760 torr. These are the three that we'll be using the most. Okay, just know this is a way that we measure pressure. I know I talked a lot, said a lot of words, but this is just 3 ways that we measure pressure. Okay, if you are interested in cars or any type of mechanics at all, you might know PSI, right? That's another way that you measure pressure, but we don't use PSI that often. Okay. So just know that we can measure pressure in different ways. You will have to convert between the 3 very often throughout the unit. So just have this handy. You don't need to memorize it, but I think it's kind of easy, 1 and 760. Okay. So that's the first property of gas that we'll be talking a lot, pressure. Okay, which is the reason why if you hold in a lot of farts, your stomach starts hurting. It's because there's more gas molecules bouncing around the inside of wherever your fart is being held. See? And it feels like high pressure. See, now you guys know. And then when you release that fart, the pressure goes down. And so there's less force in your belly. And so this hurts less. Just so you guys know, I'm not going to stop making fart jokes. That's all I'll be talking about the entire unit. Yeah. So if you guys don't like poop, I'm sorry. But it's just kind of a part of this class. Okay. The next type of property of gas we'll be talking about is volume. You guys know volume. It's just how much space it takes up. We typically measure volume in this class in milliliters, liters, and centimeters cubed. So the unit of measurement that we'll be using a lot is this. And we know that 1 milliliter is equal to 1,000. Oh, wrong way. Other way. 0.001 liters. Okay. So that's how you can convert between the 3. I'm sure you guys are familiar with liters and milliliters already. The centimeters cubed is another one. Okay. Again, the key thing is gases expand to fill their containers. And so the amount of space they take up depends on what the size of their container is. Okay. All right. Third property of gas, we all know what temperature is. It's just temperature. And I know that for us, we think of temperature of how hot it is or how cold it is. But in science, there's actually no such thing as cold. All we have is hot, because temperature actually tells us the average kinetic energy of the gas molecules or whatever you're observing. So basically, how fast are the molecules moving? The faster they move, the hotter it is, the higher the temperature, right? And so if there is more temperature, that means the gas molecules are moving faster. If they're moving faster, they have more kinetic energy. And so compared to a cold gas, if it's colder, it has less kinetic energy. Yeah.
Wait, so does that mean like you turn like iron to like a gas?
You can vaporize iron. It has to get really, really hot, but yeah, you can vaporize anything. Yeah. Okay. So in this class, I know that in America or in the US, we use Fahrenheit, but we will never use Fahrenheit. we use Celsius and another thing called Kelvin. Okay, Kelvin is called absolute temperature. And so when we are at 0 Kelvin, it's called absolute zero. I'm sure you guys have heard that term before. Absolute zero is basically when the molecules, they have no movement. Okay, when they're not moving at all, which is theoretical, but it actually technically cannot happen. We can get very close to absolute zero, but we can't actually get there because whatever we're using to cool it down, there's always going to be some movement. Okay, and there's no upper limit. Celsius, when we're at 0 Celsius, that's when water freezes, so we can have negative Celsius, but we cannot have negative Kelvin. Okay, Kelvin cannot go below 0. And again, I put it in bold, italics, underline. But in this unit, all temperature measurements must be in Kelvin. So if I give it to you in Celsius, you just add 273.15 and that'll get you to Kelvin. Okay. All right, so I know that was a bunch of information. I kind of just did a word vomit, but let's start doing some conversion. So let's look up today's weather. Let's look up the average temperature today and let's convert it into Kelvin. So I'm gonna look up weather in Long Beach. Let's do Celsius. So if we look at the weather in Long Beach, it is 64 degrees Fahrenheit. But again, we don't care about Fahrenheit in this class. So that's gonna be 18 degrees Celsius. So let's convert 18 degrees Celsius into Kelvin. Okay, so take about 30 seconds to do that. I know this is pretty easy, but I want you guys to get used to converting from Celsius to Kelvin because we will be always using Kelvin in this class. I know, I don't know why we use this redonkulous thing.
I was thinking about earlier today how we still use like decades and centuries, which is a 10 system, but we continue to use 8 inches.
Yeah, it's not good. I think America's the greatest country ever, but I definitely don't like our measurement system. All right, anyway, 18 plus 273.15, 18 degrees Celsius is 291.15 Kelvin, okay? So just make sure that if you ever see Kelvin or Celsius, that you always convert it to Kelvin, okay? If you do Celsius, it'll screw up your answers a lot. All right, any questions before we move on about pressure, volume, and temperature? Huh? Okay, yeah, just add to the Celsius. All righty, let's move on. So like I said, gases are kind of interesting because the properties of gases are intertwined with one another. So let's think about it this way. If you heat up a gas, they move faster, right? So if you heat up a gas, do you think there's going to be more pressure or less pressure? So if you heat something up, it moves faster, right? If it moves faster, does it have more energy?
Yeah.
Yes. If it has more energy and it hits a wall, is that going to be more force or less force? More. So that's going to increase the pressure, right? And so gases are weird because you can't just kind of look at it because the properties are intertwined with one another. And so we always need to set, if we're going to talk about gases with other people, we need to set a standard by which we measure them. And so that's what we call standard conditions for temperature and pressure. You guys don't need to write that whole thing. We just say STP. Okay. And so when we talk about gases for this class, we will always be talking about them in STP. And that's when the gas is at 1 atm of pressure and the temperature is going to be 273.15 Kelvin, so 0 degrees Celsius. Okay, that's where we want to talk about gases because if one person is talking about it at STP, but if one person is talking about it when it's warmer, the gas is going to behave differently. And so in order to communicate intelligibly and be on the same page, you need to define how you're talking about the gas. And so we always talk about it in terms of STP. All right, and then the fourth property of gas is just moles. This is just how many molecules, how many moles of the gas we have, and this is just basically what we've been talking about. Okay, we use molar mass, convert between moles. And those are the 4 properties of gases we'll be building everything off of. Sorry guys if that was a lot. I kind of went through it really quickly and just gave you a lot of information. But just know the 4 things about gases that we'll be talking about constantly are pressure, we got volume, we got temperature, and we have moles. Okay, pressure is how much and how hard the gas molecules are hitting the walls of their container. Volume is how much space they take up. Temperature is how fast they're moving. And moles is how many molecules of the actual gas there are. Okay. Alrighty. So with that being said, we are going to be looking at, we said earlier how the properties of gases are interconnected with one another. And so a bunch of very smart people figured out how we can put them into equations so that, like you guys love to do, we can do math with it so that we can predict how changing one property changes the other, okay? So there are a bunch of gas laws. You guys don't need to memorize them, but I do think that it's important that we figure out how we got these gas laws to begin with, okay? So let's think about it this way. Okay, so physical properties of gases, they're related to one another, which means if you change one property, a different property will change with it. And so the gas laws are equations that we use to calculate how a gas will change if one of the properties are changed, okay? So the first one is called Boyle's law. And every gas law has a supposition, and here it means that we need to keep it at the same temperature. You can't change the temperature, okay? So Boyle's law basically means if you increase the pressure, the volume will go down, which kind of makes sense, right? So if I had like a ball, right, this ball is filled with air. If I increase the pressure on it, if I push it, it's gonna get smaller, right? Same thing with the balloon. If you hug a balloon, the volume will get smaller and smaller and smaller. And so the equation that we use to describe that is this one right here. P1 V1 equals P2 V2. Very similar to that dilution equation we talked about. M1 V1 equals M2 V2. But this is a formula for Boyle's law. And so one way we can think about it is if you have a balloon, right? And you let a balloon go into the sky, as it gets higher and higher, there's less gas molecules there. And so the balloon will get bigger and bigger. And then eventually it'll pop. But that's Boyle's law. Okay. Any questions about Boyle's law? Pretty simple. You increase the pressure, the volume goes down. All right, that's the first gas law. Second gas law is Charles' law. And Charles' law supposes that there is constant pressure. Okay, and Charles' law tells us if you increase the volume or you increase the temperature or vice versa. So easy way to think about it is if you have a balloon and then you heat up the balloon will get bigger. But if you cool the balloon will get smaller. So here the temperature is going up, which makes the volume go up. Here, the temperature is going down, which will make the volume go down. Okay, so I don't know if you guys have tried this, but if you put a balloon in your freezer, when you take it out, it'll be a lot smaller than when you put it in. And it's because the gas molecules are moving less or slower, and so the volume will go down with it. And this is the formula for Charles' law. And we'll be using these in problems in just a second, so you can either write it down or have it as a reference. But just know Charles' law is you increase the volume, you increase the temperature. You guys look so entertained right now. Is it because I'm not making any fart jokes right now?
Yes.
Okay. We'll think about it. So, you know, I actually had a little thought experiment with this. Like if I really had to fart, right? And if I went inside a freezer, would that pressure decrease, right? Because I'm getting colder. Mr. Pepik, I need your opinion. So we're talking about Charles' law, okay?
Charles' law.
Okay,
I don't
Charles'
know
law.
what Charles' law is.
Okay, yeah, you do. Okay,
Yeah,
so
which
Charles'
one?
law.
Volume temperature.
Yeah, so let me. It's a thought experiment. I need your opinion, okay? So let's say that this is me, okay? Little tubby guy, and you know, like chunky guy. Okay, so inside let's say I'm holding in a big fart, right?
Okay.
And so there's
Or
gas
a
molecule.
baby.
Okay, yeah,
fart.
or my baby is holding in my fart, even though I can't have baby. But so the gas molecules exert a pressure in my belly, right?
Yeah.
The more fart you hold in, you increase the pressure, right?
I would think so, yeah.
Yeah. Let's say I walk into a freezer. Okay. This is cold. Okay. Would that, if I stayed in the freezer long enough, would the pressure in my stomach go down from the fart?
No, I'm gonna have to say that the question I need to clarify. Does long enough mean that you could just sit there and freeze
So yeah, without me dying.
without you dying?
Yeah.
Ah.
Because I know
without you
my
dying,
body tries to maintain my body
your
temperature,
temperature-
but
is
it'll
your
still
body-
go down.
Is your body temperature dropping?
I mean, it'll go down a little bit at
Fine,
least.
so you're
Yeah.
gonna go from 98.7 to
Yeah.
maybe 96.
Yeah. Yeah.
Yeah, the volume would decrease.
So that pressure will go down.
I would think the pressure.
So
would
guys,
decrease.
next time you're holding in a huge fart, just walk into a freezer.
Freezer.
Yeah. Or you can just fart in the freezer and come out, I guess.
There it is.
Yeah,
And the
there we
gases
go.
will.
Yeah, and the gases will compress. Yeah. Just run out of there before it expands.
When you start going on dates, like
Yes.
this, you should start make sure there's freezers around.
See, but the thing is, if you fart in the freezer, right, it'll slow the expansion of the gas. So it'll stay in your pants. Right? And then you don't want to take it back out to your date.
Now you're talking confusion. Hey, you know what? Sometimes you crop dust.
Yeah. Hey guys, just fart. Just fart. It's okay. They need to
guys
love you
know
for
your
who you
teacher's
are.
crop dust, right?
Yeah.
You guys know what crop dusting is?
Hey yo, I ain't gonna lie. Sometimes when I'm walking past the desk, I fart and I just walk away real quick so that
That's
they can
called
blame it
crop
on
dusting.
someone else.
That's crop dusting. You just kind of leave that fart, and then you get back up here. You're like, damn, and you're like, damn, dude, come on. It was you the whole time.
Yep. And then he who denies it supplies it. So you can blame the person that said it wasn't them.
That's right.
All right. Next gas law is Gay-Lussac's
So
law.
for us, it was he who smelt it.
Oh, that one's good. He who smelt it dealt it. I like that one.
But I like yours as well.
Yeah. Huh?
You guys heard that one?
No, I grew up with he who denies it supplies it.
I like that.
Yeah. Anyway.
In our family, it's actually a sense of pride. So my son always claims the difference.
Oh, smart man. All right. Next one is Gay-Lussac. I don't even know where we went. Guy-Lussac. Sorry, I like saying that. Okay, so this supposition is that we keep the volume the same. And so let's say we have like a metal container and we sealed it so that the container can't get bigger or smaller. If you increase the temperature, the pressure will increase and vice versa. So if we had a container like this, you heat it up, the gas molecules will move faster, which means the pressure will increase. And this is going to be the equation that describes that.
Has anybody ever done that? Anybody ever used that to increase the pressure inside a container? Ladies? Ladies usually have done this. I don't even realize it.
What do ladies do?
Well, when do you guys ever use, do you guys use hairspray? Probably not as much anymore. Do you guys still use hairspray?
I use
Do you guys
hairspray.
know what hairspray is?
Oh, that's actually a good
Is it-
example.
Or shaving cream, but guys usually haven't been using shaving cream yet.
Or spray paint.
Or spray paint.
Have you guys ever had like a spray bottle and then you spray? Do you guys know, well, how does the bottle change? How does it feel? How does the feeling change?
Oh, there's less like more.
Come on, taggers, let's go. Let's hear it.
Yeah, it's okay if you do graffiti. Have you guys ever noticed the bottle gets colder?
Yeah.
Yeah, the bottle gets colder. It's actually because of this law. And so if you have a container, we have gases in here, right? There's a certain pressure. If you release some of the gas, right, what happens to the pressure?
There's less.
Yeah, there's less gas in there, so there's going to be less pressure. And so when you touch it, the temperature goes down to it's colder. And so that's the reason why if you use a spray bottle and you let some of the gas out, the temperature, it gets really cold. It's because you're decreasing the pressure inside of that container.
Expanding gases.
Yes, sir.
You can do it with the opposite direction. If you need just that little bit more of hairspray, you're like, oh, I just need 1 minute, little squirt. You just take your hair dryer and you do the hair dryer on the bottle, or you put it underneath hot water that heats up the bottle, heats up the molecules inside, and you can get an extra couple of spurts. That's what I.
That's smart. Now I have another question for you, Mr. Papik. Let's say I'm holding in that fart again, this hypothetical fart.
Back to the part. See, now in my class, it's about giving birth. But I
Oh.
might change it.
See, well, you're a lot more cold. It's because you have kids. I don't have kids
Yeah,
yet.
so, yeah, I
Yeah.
guess.
But anyway,
Farts.
I'm holding in a fart. There's a lot of pressure. when I release that fart, does the temperature inside my whatever the fart container is called go down?
Your colon?
Oh yeah, my colon. Sorry guys, this is why I teach chemistry.
I don't, I don't know what else you can
I know that the colon will get smaller,
It
right?
does, but I actually I don't know the physiology, but when the sphincter releases that that gas, I think you're dealing with a volume change.
Mm-hmm.
So I don't know if that would negate the temperature change.
Do you think there would be a small temperature change?
There's a possibility,
That's
but
true.
I don't know the answer.
So if I held in that fart, let's say I was in Alaska and it's really cold, would holding in a fart help me maintain my body temperature? Because when I go camping, it's real cold sometimes at night, and I don't know whether I should release that fart or
Well,
not.
once you're in a sleeping bag, you do, because you get that hot gas in your sleeping bag. It warms you all up. It's hard to breathe.
That means
Then you
if
breathe
you're
on
releasing
yourself.
hot gas,
That's true.
then that means you're getting colder, no?
Hey, if somebody can tell me the right answer to this, I'll give you extra credit.
There it is. Oh, wait,
There we
okay.
go.
Now, when Mr. I don't know how much information you give about your personal life, but we went camping this summer,
We did.
and
I slept
think,
next to Mr. Pepe.
I think that we I don't know if there was some gas exchanging.
Did you fart?
Probably did. I mean, you're camping,
Dude!
you're in the mountains. That's what
Yo,
you
I
do.
sleep with my mouth open.
Don't we
Yeah,
all?
what's up?
So when you breathe in air, it's the same one.
So your lungs will expand, and so the volume will change. So this law won't apply there directly. Yeah.
Because it's for constant volume, so you
Yeah.
can't change the container size.
Yeah, the container can't change.
So when you're cold in the Arctic or something, or the amount you're breathing
You're really you start with your
So you set off a bunch of
Oh
stuff.
yeah, okay, we gotta move on. Yeah, so
in. You're hyperventilating.
yeah,
Your heart rate
these laws suppose that there's a constant one of the characteristics, right? But in your scenario about Alaska, right? As you breathe, you're constantly changing the pressure, right? Inside your lung, you're changing the volume, you're changing the temperature, and so these laws won't apply directly. We can look at it a little bit more in detail after we look at some different laws. But these laws we can't apply them in real life situations because usually we are changing all three
Now,
of the
I am gonna take you on a
properties.
tangent. I don't know if there is a I don't think there's a pressure change
When you're breathing out.
or in.
Isn't there a pressure change in your lungs?
I don't think so, because it's open to the open air. I think that the pressure remains the same.
It's a good question. You can let me know. Yeah, you're smarter than me,
But
so
I
you can
know
figure
that,
out. Let
you
me
know, the
know.
diaphragm, drops, which creates a negative pressure around your lungs in the whatever the little areas around your lungs. It
Thank
does
you.
have negative pressure, and that's what expands your lungs. But I don't think that inside your lungs there's a pressure change.
Yeah.
But there must be, because you're increasing the volume.
That's true.
But air is filling in that gap.
That's true.
I don't know if it's.
All right. Well, anyway, guys, I know that we are talking about a lot of tangents, but we do need to get through some problems. So let's move on. We'll pick up that idea in a sec. Okay, and so we can actually put these laws together and write something called a combined gas law. It's going to be this formula right here. And this is where you change two of the properties, and then we can calculate how the third one changes. Okay. So just have those four gas laws in your back pocket. You can have it on your screen, written in your notes. And the key, for this unit, we'll be figuring out, hey, which gas law do I need to use based on the variables that are given to me. Okay, so we're going to take a look at question 5.2, and I want you guys to actually try to figure out which gas law you will be using to solve this problem. That's the first thing you want to figure out. And the way that you can do that is figure out what variables you have. And then based on what you have, you can figure out what gas law you want to use. Okay, so I want you guys to take a minute to do that. Figure out which gas law you're going to use.
Do they memorize Charles Boyle's?
I told them they don't have to, because if they understand the KMT,
I don't think
yeah,
that would be a question.
it's not going to be on the test. Yeah. You just need to know the kinetic molecular theory. Yeah. Okay. So try to figure out which gas law you would want to use here, okay, based on the information you got. Is it colon where your poop is too?
Yeah.
Oh my gosh. Oh, so colonoscopy is when, oh,
Do you not know that?
dude. Well, I try not to think about colonoscopies on a daily basis, you know. I like things coming out of there. Yeah, what's up?
Okay, so for the colon, whenever you hold in gas, it does make a temperature change, but it's in a major. Whenever you release
Yeah, I would assume it's not a huge temperature change. Yeah.
Yeah.
Yeah, because you want to maintain homeostasis.
If you could, because there's nothing theory, there's nothing pressure, because that takes fire.
Yeah, but I think your colon would burst before you get to that actual pressure.
Superhuman colon.
Okay. Like Superman's colon.
Exactly.
If Superman held in his fart so long that the pressure just increased so much in there.
You could fire fire.
Yeah, there needs to be oxygen in there for a combustion to occur. So I don't
Get
know.
all over our body.
I don't know. See, but the thing is, now we get into the whole concept of limiting reagents, right? Is there enough oxygen and how much fire would it actually, like how much
What if,
fart would Superman need to hold in?
what if Superman like breathed in on a crap load?
Hey, you know what? You guys can figure this out. Okay, moving on. So you guys are just as weird as me. So, okay, so let's talk about the gas law. Here we have volume, right? We have volume is 2.4 liters and pressure is 1.5 atmospheres. Okay, and now it's asking us what volume would the gas occupy at 4.9 atmospheres. So we're looking for volume, and we're saying that the system changes to 4.9 atmospheres. So in this situation, what is the gas law that we should use?
The Boyle.
Yeah, Boyle's law, right? And it's because Boyle's law is P1 V1 equals P2 V2. And if you notice, the variables we have are 2 pressures and 2 volumes. And so all you have to do is plug it into this equation. The first pressure was 1.5 atm. The first volume original volume was 2.4 liters. We're looking for V2, so we just plug in P2, 4.9 atm. And then from there, it's just simple algebra. Okay, so I'm gonna pull up my calculator, and all we need to do is plug and chug. So on one side, we'll do 1.5 times 2.4 divided by 4.9. That'll give you 0.73, and I'll round that up to 5. Okay, so the final volume will be 0.735 liters. Okay. So what that's telling us is that we started off with a container that was 2.4 liters. The pressure that was being exerted in there was 1.5 atm. If we increase the pressure inside, or if we increase the pressure on that system, then that means it'll get smaller. It will end up becoming 0.735 liters because we're exerting more pressure on it. Okay. Here it was exerting 1.5 atm, and then we increase that pressure. We get that down to 4.4. We get that down to 0.735. Okay. And that makes sense just basically when we visualize it, right? You start increasing the pressure on something, it's going to get smaller. All right. Any questions about that one? All right. We'll do one more and then we will move on to the next topic. Okay. So we'll try this one. A 12-liter container of hydrogen gas is collected at 3.8 degrees Celsius. Want you to find the volume of gas if it drops down to negative 39.9 degrees Celsius and the temperature or the pressure is constant. Okay, so I want you guys to figure out which law you want to use and to also calculate that out. Alrighty, guys. So if you guys are finishing up, feel free, and then you can just check your answer at the end. But for the sake of time, let's go over this. So here you should have identified that you have V1, T1, and T2, and the question is asking for V2. And so obviously, this one is going to be Charles' law. Okay, and Charles' law is V1 over T1 equals V2 over T2. And so what we need to do is we just need to plug in our values. So we'll put 12 liters on top. Can I plug in 38.8 by itself? No, I need to change it into Kelvin, right? Because you can't just use Celsius. Okay, make sure you guys keep that in mind. So I need to do 38.8 plus 273.15. That'll get me 311.95 Kelvin. Okay, so 311.95 Kelvin. Okay, and that'll give me V2 over T2, which is going to be negative 39.9, okay, plus 273.15. Okay, and this problem actually tells you why we need to turn everything into Kelvin. If you plugged it in just as Celsius, you would end up with a negative number, right? And you can't have negative volume. The smallest volume you can have is 0. Yeah, what's up? Excuse me. That's if they were both negative, but here only one of them is negative. So yeah, if we had a like let's say this was a negative number, if you multiply it, you would end up with a negative volume. That's physically impossible. Yeah. Okay, so here we just need to solve out for V2. So we can do 12 divided by 311.95, and then multiply that by 233.25. And so your final volume, V2, is going to be 8.973 liters. Okay, yeah. I recommend not using Celsius at all, because even then it's not going to work out, because once you turn into absolute temperature, the ratio will change. Yeah, so never use Celsius. All right, any questions? Okay, we have one last gas law we're going to look at today, and then we will be all done. Okay, and so gas law number 5, you guys know this person's name. It's going to be Avogadro. You guys remember Avogadro's number? It's about moles. He's the guy that said that, hey, in 1 mole of something, you have 6.022 times 10 to the 23rd, right? This guy also figured out a gas law, okay? And the gas law is that if you want to keep constant pressure and temperature in a container, so let's say you have a container filled with gases and you want to make the container bigger, okay? But you also want to make sure that the pressure stays the same and the temperature stays the same, okay? In order to make that container bigger while keeping the same pressure and temperature, you also need to increase the moles of gas, or how much gas you have in there. Okay, so if you want to make a container bigger, but keep the same pressure, keep the same temperature, you need to add more gas in there. Yeah. Yes, yes, that's exactly right. Yeah, sorry, I have to think about that, because yeah, inside your lungs, you want to make sure the pressure stays the same, because you don't want your lungs collapsing or blowing up. You want to keep the temperature the same so you don't get too hot or too cold, but you want to make your lungs bigger so you can take in gas. You need to increase the amount of gas that goes in there. That's a great observation. Man, you guys are so smart. Okay, and this is the formula. Okay. Basically, in order to keep the pressure temperature the same, the relationship or the ratio between the volume and the moles need to stay the same. Okay. Yeah, N just means like how much gas. So moles of gas, which you can convert to grams of gas, right? It's just basically how many gas molecules you're putting in. All right, last problem, and we'll be done for today. Okay. Okay, I want you guys to take a look at 5.5. Okay, see a balanced chemical equation. So in this reaction, hydrogen gas and it's not nitrogen gas, it's oxygen gas. Okay. And oxygen gas, they react to form water vapor in this reaction. Okay, let's assume that at a certain temperature and pressure, you got 5.74 liters of hydrogen gas and it reacts with 2.87 liters of oxygen gas. If we use all the reactants, okay, how much water are we going to make if the temperature and pressure stay the same? So let's start off by just writing down the values that we have. 5.74 liters of H2 gas and 2.87 liters of oxygen gas. Okay, let's start by writing our values. Okay, so basically Avogadro's law tells us that the ratio between volume and moles stays the same, okay, if we want the same pressure and temperature. And so the ratio, we get the ratio from the chemical equation. So if we start with 5.74 liters of H2, okay, if we take a look at the chemical equation, it tells us that the ratio between H2 gas and oxygen gas is just 2 to 1. Okay, so the ratio is 2 to 1. Okay, what that means is if we want to calculate how much water is going to be produced while keeping the same temperature and pressure, all we need to do is use this ratio. Okay. Oh, sorry, it shouldn't be O2, it should be H2O, my bad. Okay. So if you guys notice, if we're looking at H2, it's 2 moles to 2 moles. But then if we take a look at the ratio between O2 gas and water, it's 1 to 2. Sorry about that, guys. Okay, so that means the ratio between O2 is 1 to 2. And so we just plug this into our calculator and it'll tell us how much water can be made while maintaining the same temperature and pressure. And so we just do 5.74. We just multiply that by 2, divide by 2, that'll give us the same answer, 5.74 liters of H2O. And then if we do the same thing with the oxygen, 2.87 times 2, we get the same number, which tells us that this is the right ratio that we're working with. Okay. So basically Avogadro's law tells us you want to keep the same temperature, same pressure, you're going to have to change, or the ratio between the volume and moles have to stay the same. Yeah, what's up?
So what happens if they were different? Like, would we have to like find something else, or?
So if the temperature and the pressure changes, then we can't use Avogadro's law anymore. It only applies if it's about same temperature and pressure. Okay, and that's pretty much it for today. Any questions, guys? All righty. I know that was a lot of information after a test. But yeah, that's going to be it for gas laws. Just make sure you guys are familiar with the characteristics, and then we'll get started with some other things next time we meet.